All right, so a little preview of chapter 6. Just to try and get us 15 minutes closer to being on track. So chemical composition. This is where we're going to talk about now. We've covered how to name compounds. We've covered what compounds are. We've even talked about now calculating what formula mass is, where we take all of the atoms together, add them up. But how do we actually count atoms? And how can we do that in a useful way? Because remember, atoms are so tiny that in a single grain of sand, there are more atoms than there are grains of sand on the largest beach. If you took a pebble and you increased the size of all of the atoms in that pebble to the size of the pebble, it would be a mountain larger than Mount Everest, right? So these things are super, super tiny. There are trillions and trillions and trillions and trillions of them in just 1 gram of something. So we have useful ways of talking about them, aside from using those enormous numbers. Sodium is an important dietary mineral. It's in food. Most of the time you get it as table salt. You need it. It regulates body fluids. Eating too much of it can lead to high blood pressure. But it's potato chips are just so delicious because of the salt. So the FDA recommends a person consume less than 2.4 grams, which that's a lot of salt. That's a pile of salt. Or 2,400 milligrams of sodium per day. But the mass of sodium that you eat is not the same as the mass of sodium chloride that you eat, right? Because part of that sodium chloride is chlorine, not just sodium. So this FDA recommendation is for sodium, not just sodium chloride. So how do you figure out how many grams of sodium chloride you could consume and still stay below that FDA recommendation for sodium? And again, we've given the chemical formula. We have the chemical formula from the name, sodium chloride, which is NaCl. So there's 1 sodium atom, 1 chlorine atom, and all we care about here are all of the sodium atoms. So since the masses of sodium and chlorine are different, looking at the periodic table, chlorine is 35, sodium's 22. So even an individual sodium atom is going to be lighter than a chlorine atom. The mass of sodium and the mass of chlorine and sodium chloride is not clear from the formula alone. So we can't just say that half of all of the sodium chloride that we eat is sodium and the other half is chlorine. So you have to calculate the amount of a constituent element in a given amount of a compound. So one of the ways you can do this is using the formula along with the formula mass or atomic masses. So for example, if a mining company needs to know how much iron is in a given amount of iron ore, they can use this chemistry, this math, to figure out how much of a ore is actually iron atoms. Or estimating the amount of chlorine that's in a chlorofluorocarbon, which were used as refrigerants for a long time. That's what Freon was. Can't get Freon anymore. Don't like the way these are organized. All right, we're going to come back to this idea of the sodium. First, though, we're going to talk about this relationship between the different masses. Right, so the whole purpose here that we're trying to work towards is how do we determine how much of the mass of our 2.4 grams of sodium, how much actual table salt can we eat? It's going to be more than 2.4 grams, but it's not going to be double. It's actually going to be a little more than double. Another way to think about this is similar to how hardware stores sell nails by the pound. All right, so if you need hundreds of nails, you're not going to have the hardware store clerk count out nails one by one and give you, exactly 1,000 nails counted out by hand. The easier way to do it is if you know how much one nail weighs, then you can say, oh, well, this many nails will be in a pound of nails. So that's similar to asking how many atoms are in a given mass of an element, because you could have small nails or you could have large nails, right? You can get more small nails in a pound of nails than you can have large nails in a pound of nails. So if a hardware store customer buys 2.6 pounds of medium-sized nails, and a dozen nails weighs 0.15 pounds, how many nails did he buy? You guys ready for more unit analysis? Okay, let's break this down. So we got 2.60 pounds of nails. And we know 1 dozen, 12 nails, equals 0.150 pounds. So if we start with 2.60 pounds, actually I'm going to start using this. So this is the same thing as writing everything out, this times this fraction times this fraction, but we're going to put them and represent that as boxes here. So we've got our 2.6 pounds of nails, and we're going to put 0.150 pounds on the bottom and 12 nails on top. That's our conversion factor between nails and pounds. And then, because this is the first time I've done this, this is the same as doing this. So our pounds of nails will cancel out, and we'll just be left with the number of nails that are in that 2.6 pounds. So 2.60 times 12 divided by 0.150 is calculators in scientific mode. So this is 208 nails. Right. Even with all the time that we took here, it's probably faster to do that than it would be to calculate out individually 208 nails. You can see here too that if we had smaller nails, then 12 nails would weigh less, and we would have more nails in that 1 pound. Right? Or for the same 0.15 pounds, you could get more nails in there. So with atoms, we're going to be doing exactly the same thing, except we're going to say how many atoms are there in a gram? Or really what we do is how many grams of atoms are there in 1 mole? But atoms are too small and too numerous to count individually. So even if we wanted to, you couldn't count out individual atoms. And if you did, if you could see atoms and counted them for 24 hours a day, as long as you lived, you would barely begin to count the number of atoms in something as small as a grain of sand. Actually, yeah, this is the last slide. We're going to end on this slide. So let's see how many atoms you could count if you lived the average lifespan of, like, let's say 83 years. So if you lived for 83 years, how many nails do you think you could count, like, per second, per minute? Probably count like 5. Let's say you count 5 nails every second. You're fast. 5 nails. So 5 nails per second. And now 83 years times 365.25 days in a year, that's 30,000, times 24 hours in a day, times 60 minutes in an hour, times 60 seconds in a minute. That's a big number. So that is 2.62 times 10 to the 9 seconds times 5. So you count 1.31 times 10, or sorry, not nails, atoms. 1.31 times 10 to the 10 atoms in 83 years, assuming that you did that for 24/7, every single day, 5 atoms a second. In 1 gram of carbon, so like if you had 1 gram of like pencil lead, there would be, let me do it this way actually. If in 12 grams, so if you had 12 grams of pencil lead, that would be 6.022 times 10 to the 23 atoms. So if you had 6.022 divided, or e to the 23 divided by 12. Yeah, so 1 gram of pencil lead would be 5 times 10 to the 22. So that's not half. You wouldn't count half of them. You would count about, times 10 to the 10, that's just over a billion. So you'd get to like 10 trillion. But there are 10 trillion trillion. So there's a trillion times more atoms in 1 gram of pencil lead than you could count in an entire lifetime if you counted for 24/7 for 83 years. So this is why you can't just count them out. All right.